in order to kind of put this in perspective, this is what the whiteboard looked like on last Friday, spring break. And we talk about, and I'll kind of, again, try to kind of put things in perspective, get a running start. But all matter is made up of atoms and occupies space, and matter can either be a mixture, and I think we talked about this, or it can be a pure substance. And if it's a pure substance, it can either be an element, or CPD is my version of compound. If it's a compound, it can either be a molecular compound or an ionic compound. And that's actually probably what that board says. Okay? And we kind of compared and contrasted the two different types of compounds. If you have an example of a molecular compound, an ionic compound is NaCl. You have two very common compounds for everyday life. And we talked about, let's go here, this Greek letter, this X-looking thing, that's actually what we call electronegativity. And if you look at an ionic compound, the sodium actually has a relatively low electronegativity, which means it's going to not just share its electrons, but an electron is going to be transferred to the chlorine. That leaves the sodium with a +1 charge. It's what we call a cation, and the chlorine is what we call an anion. And so the deal is if we go ahead and come up with electronegativity difference, that's going to be equal to or exceed 1.7. That's where we get that electron transfer. So just kind of reminding you how that all works. Because now I want to focus on just ions and ionic bonds. So once you have your cation, your anion, then this ... that is the ionic bond, ionic chemical bond between those two ions. So in order for this all to work, we need to kind of revisit something about electrons. All electrons are not created equally. And a few, last unit, you guys came up with electron configurations, and they kind of petered out. The one with the highest N, those are our valence electrons. Okay, we call that all the valence electrons collectively are called the valence shell. Okay. So, and I think it's on the next slide. So it's these outer valence electrons that are important because they are the ones going to be transferred, or they are actually, when we talk about electrons being shared, they're the ones doing the sharing. And it's kind of convenient because if we want to know how many valence electrons an element has, we can, if it's a main group element, all we got to do is find on the periodic table and look at the group number. So these 1As all have 1 valence electron, 2As, 2 valence electrons, 3As, 3 valence electrons. Now, why does an atom want to lose electrons, or gain electrons? It has to do with getting this, what we call rare gas configuration, sometimes called a complete octet. You can kind of see the octet, and I think I've been talking about this when we did the electron configurations. The NS2, NP6, where the N is just some principal energy level, principal energy level. And the superscript 2 and 6, if you add that up, you get 8. And so that's kind of the octet that these rare gases have that make them so inert. So when atom A and atom B are going to chemically bond, whether they're sharing electrons or an electron is going to be transferred to form a cation and anion, it's all about getting, or oftentimes, to try to get that complete octet rare gas configuration. So talking about ions, we can have ions that are only one atom. Okay. We can, and the word mono means one, so monoatomic ions. It just means an ion is one atom. Versus polyatomic ions. Okay. So a monoatomic ion means something that has an ion means it's not electrically neutral. So that means, and we need to think of the protons as being embedded in the nucleus. Protons can't come and go, but electrons can come and go. So if it's charged, it's electrons that are kind of gone. So what we're going to see is that, and it's on the next slide, but I'll put it on this slide too. I'm going to put metals next to cations because that's what forms cations, are the metals. And we see this example here with sodium chloride. The sodium, I'll just kind of use that as an example. Which color do we want? So sodium, if I find it on the periodic table, it's atomic number 11. So I'm going to put, this is its nucleus. This is my sodium nucleus. Oops. I have to be a big nucleus so I can put the word 11 protons in its nucleus. And I don't care about neutrons for now. But sodium right off the shelf is going to have, if it's neutral, it's going to have 11 electrons. Okay, configured a certain way. Now, as it loses one electron, so one electron transfers possibly to a chlorine atom that wants it. Now it's left with still 11 protons, but now it has only 10 electrons. So you're like, 11 pluses, 10 minuses, that's why it has a net +1. And we can look at the chlorine here. It's got, in its center, it's got 17 protons, and it's neutral, goodness, and it's neutral, it's going to have 17 electrons, but as it gains an electron, now it still has 17 protons, and now it has 18 electrons. Like, you compare the two, you're like, it's got one extra negative particle, so that's why it's a -1. So the metals form cations, and the nonmetals, such as chlorine, form anions. And what an anion is, it's a negatively charged particle. What a cation is, it's a positively charged particle. There's different ways to kind of help remember this, but I think of like cat, you know, the plot. This is almost like the T in cation kind of reminds me of a plus. And I don't know how you remember anion, but it's negatively charged. Okay, so yeah, like this slide says clearly, the metals tend to form positively charged cations. In other words, they lose, I can never spell lose. They lose an electron or electrons, okay? And the nonmetals form anions. They gain an electron or electrons. And so kind of having familiarity with the periodic table and that jag that separates our metals from our nonmetals is important. This is kind of like a deja vu sort of thing. We did this before where we talked about isotopes, and we said we can kind of do this shorthand indication of an isotope by X would be the symbol of the element. In the upper left-hand corner, we put the big number, the mass number. And remember, just make sure we're all on the same page. This has to be an integer, a whole number, and it's literally looking at the nucleus and counting number of protons plus the number of neutrons. And of course, atomic number is the number of protons. And now we need to throw into the mix the fact that it may, if it's neutral, you won't see anything in the upper right-hand corner. But if it's a cation, you'll see plus and whatever charge it is. If it's an anion, you'll see negative and whatever charge it is. Okay. So cations are going to have 3 nuts. The symbol for mass number is A. The symbol for atomic number is Z. You're like, really? Why did they do that? I don't know, but they did. So we have a cation looks like this. So the N would be the how much positively charged it is, and here this N would be how much negatively charged this anion would be. So one of the things we did before was, if you're given the shorthand notation of an isotope, we said you can knock out protons, neutrons, and now we're going to, and electrons, but they were all neutral before. Now we're going to kind of revisit this idea and also knock out electrons. So if we had this information about calcium, do you have the answers for these yet? Yeah. Okay, cool. So calcium, it's atomic number 20, so 20 protons, This particular isotope is mass number 39, that's protons plus neutrons, and it's a +2 charge. So can you help me out? How many protons would it have? Very good. How many electrons would it have?
18.
Perfect. That 18, and you took that by recognizing it has to have 2 less electrons than it does protons. Perfect. How about neutrons?
19.
You got it. Perfect. So how about this one? This is chloride ion with a -1 charge. How many protons?
17.
Perfect. How many electrons?
18.
You got it. Neutrons? 19. Sometimes I do that in my calculator, but very good. Yep, you got it. Just kind of building on something else we talked about. Perfect. Okay, so this will be due Wednesday. First day of spring, in theory. I don't know. It's like it varies. It says the equinox on my calendar, so I don't know. And I think that it kind of floats around depending upon leap year and stuff like that. But it's always like our proximity to the sun, and there's equal amount of daylight and nighttime at all latitudes. But yeah. Okay. So you probably recognize the C, N, O, F, and Ne. Of course, those represent elements. And what I'm showing you here is what I call Lewis electron dot formulas. Now we're going to talk about Lewis electron structures later, but these are just for individual atoms. So when you see this, you can think of the carbon, the letter C is representing the center of the carbon atom, the nucleus, and all electrons that are non-valence electrons. So if we find carbon, we can go over here, and it's 4A. Okay, so those 4 dots represent the 4 valence electrons. Carbon. Nitrogen is 5A, it's got 5 dots. Oxygen 6A, 6 dots. Fluorine 7A, 7 dots, and neon 8A, 8 dots. Okay, so actually there's our complete octet, and you can kind of just get a sense for what's going on with the element. So whenever we talk about Lewis dot formulas of atoms or Lewis dot structures of molecules and polyatomic ions, the whole north, south, east, west has no significance, none at all. The top, bottom, left, right does not. No special significance. But we can get a sense for if atoms want to have a complete octet, you kind of see, if we kind of back off to fluorine, the fact that it's just 1 electron away from getting a complete octet. And that's why all of the halogens tend to form say a -1 charge, pick up 1 electron. All of the 6A elements, including oxygen, tend to pick up 2 electrons, form -2. Nitrogen pick up the 5A, pick up 3 electrons, form a -3 charge. I think that you were maybe Gabe asked the other day, what does carbon do? Carbon can kind of go, it can kind of do multiple things. A little bit of semantics. The textbook would call the previous slide Lewis structures, but I call the previous slide actually electron dot formulas, because it's just an atom, or it could be an ion. And I reserve the term for Lewis structures as something like a polygon, so that's okay, just so you know. Okay, so helium, atomic number 2, and actually it's over here, it's an 8A element. It winds up with rare gases, and it doesn't have a complete octet. It is a rare gas. It's inert. It doesn't wind up. It's happy. Okay. If we were to come up with how the electrons are configured, those 2 electrons are configured. Remember, you can use the arrow diagram, but it just looks like this: 1s2. Okay. So this one, it says n is equal to 1. It's talking about the subshell. Okay, sodium. Sodium's a little different. Sodium's a 1A, so we would look at its Lewis electron dot formula would look like this, where that's the 1 valence electron. It loses 1 electron, and now it looks like this. And I'll kind of show you. I think I have this coming up, but let's pick on sodium. Sodium's got 11 electrons. Whew, goodness. And I think you guys did pretty well on this part of the test, where we could say how those 11 electrons are configured, and it would look like this: 1s2, whoops, 2s2, 2p6, and then 3s1. So that 1 valence electron is like this. And all this is saying is, once this one goes away, that actually these 8 electrons are what's being represented here. Okay, so we say now it's, instead of having 3s1 electron in its valence shell, now it actually has 8 electrons in the energy level 2. Yay. Yay for the sodium plus 1 cation. We could pick on fluorine. Okay. And to me, when the nonmetals pick up electrons, they're a little more intuitive. Okay, so it went from, goodness, a 1s2, 2s2, 2p7, or sorry, 2p5, final answer, because it's got 7 valence electron. Now it's got 1s2, 2s2, 2p6. Okay, and actually I have a slide coming up to kind of walk you through how that works. But we can kind of see here now, instead of 7, it's got 8. And how did it do it? It picked up 1 electron, and what was the consequence? It becomes a -1 charge. Sulfur is a 6A element, so those are 6 valence electrons. I'm not going to do the configuration, but it's going to pick up 2 electrons, get a complete octet, and in doing so, it will be a -2 charge. Okay. And this is one of the things that you can see, especially the nonmetals would become like the rare gas in the period in front of it, or at the end of the period that it's in, and the metals will lose electrons to become like the rare gas in the end of the period before. Okay, so these will also be due on wavelengths. So all I meant to say was, when we were picking on sodium, sodium is in period 3, it kicks off 1 electron. And then if we look at period 2, the rare gas at the end of period 2, that's what sodium is going to be like. Kicks off 1 electron, still has the heart of a sodium atom, 11 protons, but now it has 10 electrons. So, and that would be the same with all metals. They become what we say isoelectronic. It's a term I'm going to show here in a minute. The same number of electrons as the rare gas in the period before it. So in tomorrow's lab, we're going to be combining cations and anions, so metals and nonmetals, and we're going to be making ionic compounds out of them. There are some elements that you can hang your hat on what charge they're going to form. So see, this says predictable. I don't know why I use this phrase, but I'm kind of stuck with it. Hang your hat on what charge they form. So I encourage students that if you have your periodic table handy, or if you just kind of keep this in mind for your test even, I think I might have mentioned this before. At the 1A elements, I put a +1 because that's the charge they form. The 2A metals, a +2. The 3A metals, so you have to go under the JAG for the 3A metals. So these guys, +3. And I know it doesn't show these guys down here, but I'd probably say +3. And then I go, of course, these guys don't form any ions because they're inert. They're already happy with complete octet. 7A pick up 1 electron to become a -1 anion. 6A pick up 2 electrons to become a -2. Now these would just be, it stops north of the JAG, so these are just our nonmetals. 5A, pick up 3 electrons, become -3 anion. And again, I would think you could at least have nitrogen and phosphorus, maybe not arsenic, I'm not sure, but phosphorus is a -3 charge too. So you can hang your hat on those, it's predictable. Now this is kind of one of the things that I kind of gave you a glimpse of before. So group 1A, 2A, and 3A are going to lose all of their valence electrons. Okay, and then in doing so, they'll have a rare gas configuration complete octet, but it will be like the rare gas in the period before. That's why it says N-1. So just to kind of be explicit about that, if we pick on the alkali metals, okay, all these guys are listed up there with a +1 charge. If we pick on the alkaline earth metals, all these guys listed are with a +2 charge. You can hang your hat on the charge they form. Skipping over to 3A, skipping the B elements, going over to 3A under the Jag, okay? These guys would be a +3. I guess I've only got 2 listed there, I don't know. But for sure, aluminum, gallium, indium, and thallium must do something different. I don't know. I don't ever worry about them. They form a +3, kicking off those 3 valence electrons. So to kind of see what that looks like, if we look at and I did this one as an example a little bit ago, the 11 electrons around a neutral sodium atom look like this. When it loses an electron to form a +1 cation, the one that goes is that 1 valence electron in 3s. So sometimes this upcoming unit exam will actually, I will have you write electron configuration for ions. So aluminum, it's 3A, so it's going to lose its 3 valence electrons. Here's what a neutral aluminum atom looks like with regards to electron configuration, and you can, it's just blaring. Those 3 are the ones that are going to go. So if we aluminum +3 cation, it has it stops right there. Okay, so those guys are gone. So when we go to 5A, 6A, 7A, if you have a periodic table handy, you should be thinking 5A, 6A, 7A. Well, now I'm in the nonmetals region. Okay, I know that I've got actually some metals and nonmetals, but it's mostly nonmetals. These guys are going to pick up electrons to form anions, be like the rare gas in front of them. So make sure we're on the same page there. 5A nonmetals will pick up 3 electrons, become a -3 charge. The 6A nonmetals will pick up 2 electrons, become -2 charge. And 7A will pick up 1 electron, become -1 charge. So it's just, if I was taking the unit exam over this material, I would, when I get my periodic table, right at the top, I would write +1, +2, +3 for my cations, and I usually go from right back to left again. Here, I go -1, -2, -3, just so I remember it. So let's look at how the electrons are configured with regard to the nonmetals picking up electrons. So kind of going with abbreviated rare gas notation, here's those core 10 electrons associated with the neon. Beyond those 10 electrons, here's how the 7 electrons are hanging out, 3s2, 3p5. Chlorine will then pick up 1 electron, and you can kind of see where it's going to go. It's going to join the 5 electrons in the 3p, so now instead of 3p5, it's 3p6. And we can see your complete octet there. And in picking up 1 electron now, it's a -1 charge. Let's pick on phosphorus. Phosphorus is a 5A element. You can see it's 5 valence electrons here. It needs 3 more electrons to get a complete octet. Again, it's going to keep its core 15 protons, but it's going to pick up 3 more electrons. And in doing so, now its new electron configuration, it's not 3p3, it's 3p6. So we have 3s2, 3p6, complete octet, complete set of 8 electrons. Rare gas configuration. So I mentioned this term a little bit ago. As the metals kick off electrons to become positively charged cations, and as the non-metals take in electrons to become negatively charged anions, all this electrons going and coming, we end up with these things called electronic species. Sounds almost biological, but it's not. All it means is they have the same number of electrons, and electrons are configured or hanging out in the same way. So if we kind of focus on 1s2, 2s2, 2p6, that would be neon. So you figure these guys are gaining electrons to be like neon, and then in the period after it, you figure these guys are kicking off electrons to be like neon. So all of these are isoelectronic with neon. Nitrogen picks up 3 electrons, oxygen picks up 2, fluorine picks up 1. Sodium in the period beyond it, it's going to kick off 1, magnesium kicks off 2, and aluminum kicks off 3. So they're all isoelectronic. Be a favorite term to put on that first page, which all students hate, the definitions. So here we have these. I said you can hang your hat on these. I didn't say hydrogen, but you can hang your hat on these. You can hang your hat on aluminum, and I actually threw in under aluminum gallium at least. You can hang your hat on all of these. And then these guys right here, I'll kind of just do it like this. Okay. I said, where I have the squiggle mark, you're like, which sort of cation is going to form? And it sort of depends. Actually, I'm going to have to, in tomorrow's lab, I'll kind of clarify, but I need to pick these out too. You can hang your hat on all the asterisk ones. Because you can hang your hat on silver and cadmium and actually zinc. Oh, zinc. But this is going to make more sense tomorrow, that the fact that we can have, for instance, pick on iron. The fact that iron can be a +2 or a +3, like, oh man, which one is it? Well, again, it depends. All right. So let's just say that we have something forming a cation, so it's kicking off electrons. It's always going to lose its valence electrons first. And specifically, for instance, when we got to aluminum, we had 3 valence electrons going to be kicked off, and we had 2 electrons in the 3s and 1 electron in the 3p. The one in the 3p is going to go first. Actually, we talked about this in the lowest n plus L rule. L's actually are your S, P, D, and F. So just to kind of remind you how that goes. S, P, D, and F, and that has an L value of 0, 1, 2, and 3. So, goodness. Yeah. So I have an example here, not aluminum, but I'm kind of kicking it up to actually iron. Iron is atomic number 26, and 26 electrons are configured this way using the arrow diagram or the block approach. If we were to go ahead and reorganize it in order of increasing n to kind of isolate the highest n on the end, showing you my valence electrons, notice that iron is one of those that has actually 2 valence electrons. Okay. A really common mistake is people don't think of it in terms of what I've been talking about. When iron forms a cation, when it loses electrons, these are the ones that go first. These guys, they don't go first. Okay, so the +2 version of iron cation, it's just simply going to be this minus the 4s2. Okay, so a few slides ago, I said iron can form a +2, and iron can also form a +3. So if we piggyback from the +2, the +3 version needs to kick off 1 more electron. And so here's where valence electrons wise, we have, let's see, 8 plus 6, we've got 14 valence electrons, technically. 14 valence electrons. But the highest D would be, sorry, the highest L would be our D. So that's why when we go from the plus 2 cation to the plus 3, kicking off 1 more electron, that's why you can see here we've got 5 electrons now instead of 6 electrons in the 3D subshell. Which, by the way, we kind of talked about this being kind of a happy sort of thing. All D-type subshells have, you would tell me, 5 boxes. And according to Hoon's rule, electrons spread out. So that's kind of a happy sort of situation. That's kind of... All right, so this will also be due Wednesday. Tell ya. And there's no, I mean, we're going to finish up this part, but there's no more homework due. This one doesn't hurt my brain. This one's pretty good. So you figure cations are losing electrons, and electrons are what give the atom volume. So man, it's losing so much volume, then cations will always be smaller than the parent neutral atom it came from. Anions are picking up electrons, so an anion will always be larger than the neutral atom it came from. That's cool. And then I go on to kind of do these slides just to remind you when we talk about the volume of an atom, we need to kind of talk about, let's see, I don't want to pick, let's pick on carbon. So here are my 6 protons around a carbon atom. I'll go ahead and make it mass number 12. There's my nucleus. And then I have 6 electrons out here. Actually, we kind of talked about we have 2 electrons in the 1s, 2 electrons in the 2p. Oh, glad it told me. And then we have 2 electrons, sorry, in the 2s, and then 2 electrons in the 2p. Okay, so there's where my electrons are. And we talked about how the volume is, like I said, kind of run by whatever the electrons are doing. And so we have this this attractive force between the differently charged particles, makes it smaller. And then we have this repulsive forces going on between individual electrons in the cloud, makes it larger. I mean, but it just, so if the attractive forces went out, it's going to make it smaller. And that's what happens when we go ahead and turn into lose electrons and form a cation. The fact that anions are larger means the repulsive forces are linear. Okay, repulsive forces increase, larger structure. Attractive forces, repulsive forces decrease, or attractive forces increase, a smaller structure. You're like, oh, that totally makes sense. One of the things on your previous unit exam, and again, we might kind of pull over to this unit exam, was which is larger? And you did a good job kind of finding it on the periodic table, neutral atom-wise. You told me, for instance, if it's a neutral atom, comparing these 2 atoms, you would tell me selenium is larger than sulfur. And then it's kind of the backward sort of thing. You would tell me that aluminum is larger than sulfur. They're used to. So I might throw in this idea of sizes. So here I've got sodium and magnesium. Sodium, magnesium. So metals tend to kick off electrons and form positively charged cations, and so they're going to be smaller. The PM, by the way, I think I might have mentioned before, when we talk about sizes of atoms, PM stands for picometers. So here's kind of another look at the same thing. This actually then throws in kind of showing you the attractive forces between the 11 protons in the center versus 11 electrons on the outside for a neutral sodium atom, and only 10 electrons on the outside for a sodium cation. So the attractive forces increase, making it a smaller atom. Chlorine, on the other hand, will pick up an electron And instead of then having 17 electrons, it's going to have 18 electrons. It's going to make that repulsive forces stronger in the electron cloud outside the nucleus and makes it larger. I'm not sure why I have this. This is showing you kind of for each element listed here anyway. The box shows you the neutral parent is in gold, and then the cations are in blue and the anions are in green. So the cations, the blue cations all got smaller than the neutral parent, and the green anions all got larger than the neutral parent. So, any questions? Hopefully, if you have questions, one day. Okay. Well, then we'll see you tomorrow.